Okay, so I'd like to be able to display a hex value of a certain length. Not sure. Let's see what we can do. Let's go ahead and create a file called hex.asm, and let's go ahead and put a make line in. There we go. We'll just assemble it. We'll have to figure out a test harness for it later. I'm going to export a function. So let's call that just hex. Or maybe print hex. Let's call it print hex. That seems like a better name. Alright, that's good. Let's go ahead and create a text section. So we'll start our text section out here. I'm probably going to want a little lookup table for hex values. So we'll call that hex digits. I'll give it a data byte, and we'll have those values in it. Pretty simple. Alright, so now I can refer to if I have a 4-bit hex value, I can just look for the offset into hex digits of it and go ahead and grab that. That sounds good. Print hex. Yeah, so anyway, get started on that. Let's go ahead and get some space, and let's just say print hex. There we go. Practically done. So what I want to do in print hex, well, I need to say what I'm actually doing. So I'm going to take a couple arguments. Let's see. I want to take 2 arguments. Let's be more explicit. You know what? Maybe what I want to do is write a prototype for it. So we're not going to return anything. Why would we? Print hex, and I want to take 2 arguments. So the first one can be the number to print, and the second one can be the number of digits to print. That sounds reasonable. So we'll just say value and digits. How's that? And then we can explain it down below. I don't want to be able to pass in like a 64-bit value and print some ludicrous number of digits. Really, the number of digits shouldn't ever be more than what, 16? So maybe I should say something like there we go. So now I can just throw away all the other digits, and I don't have to worry about it being greater than 16. That all sounds reasonable to me. So there's my little function prototype. I'll need that when I want to connect it to some C maybe. And there's my explanation. And it seems reasonable. So I need to now start this function. I need to do it in the normal AMD 64 calling convention way, which is to push RBP. Got to preserve that value. Later on, I will want to pop RBP, and then I'll return. It's practically written now. Now, of course, I've got to move into RBP the stack pointer. And I don't know, I'm feeling spicy. Let's go ahead and put a little tab in there. There we go. Look at that. It's beautiful. So at the end, we'll undo that. Nice and symmetric. So the first document is going to be in RDI, second one in RSI. I could put that up here. Let's put it right here. RDI is value to print, and the argument digits. RSI is the number of digits to print. Yeah, there we go. So I've already said I want to throw away up at the bottom 4 digits of RSI. So really I want to AND RSI with that. There, that throws away the bottom 4 digits. It throws away everything but the bottom 4 digits. Let's be more intent driven on our comment. There we go. Now, is that right? So let's stop and think for a minute. I really want it to be 1 through 16. So really, the value should come in from 1 to 16. And so what I really should do is dec RSI. So if it comes in 1 through 16 now, it's 0 through 15. I've corrected that, and I could increment it now. Look at this. There. Now what I've got is a value that is from 1 to 16, and that tells me how many digits I want to print. If they wanted me to print 0 digits, they should just not call this function. That's what I think about them, whoever they are. So that takes care of making sure RSI is in the interval from 1 to 16. Yeah, I like that. Now let's go with that. Now what I want to do is loop over it, pull each nibble out, convert it into a hex digit, and I've got to put it somewhere to print. I need to put it in a buffer. I want that buffer to be in some reserved memory. So let's go ahead and create a BSS section. And I'll call this buffer, and I'll reserve some bytes, and I'll reserve so a full 64 bit value will have 16 digits. I want a new line on the end. I'm going to reserve 17 bytes here. So that's the buffer that will hold the output. There we go. So now my job is to do something like loop over these values. So let's use RCX for that. So I'm going to move RCX and RCX and what? The number of digits, right? So that would be RSI. Okay, fine. So that'll be the number of digits printed out, and I'll be printing them out from the low value first. So I really need to make sure down here that I put them in the right place, or that I print with the correct offset. That might be okay. I'll have to figure that out a little bit later. I don't want to print a bunch of garbage that's in front of it. So we'll just not worry about that for right now. So this now, RCX now holds the number of digits to print. So let's go ahead and make a little label. And there's our top label. That'd be the top of our loop. And what do we do in the loop? Well, in the loop, we want to get the low nibble out of our value, which is RDI. So let's go ahead and a number of ways to do that. I'm guessing a way to do it is to just go ahead and say move, and let's use REX for this and RDI, and then we will AND RAX with the low nibble. There. So becoming a common theme. So now REX holds the low nibble of RDI. While we're here, we might as well go ahead and get rid of that rest of the stuff. So we'll shift right, RDI, and 4. That'll throw away the bottom 4 bits of RDI. So next time we come to the loop, we'll look at the next nibble. So now REX holds the correct nibble. And we want to now convert that to a hex digit. So what I really want to do is come down here to this location and offset it by RAX. So I want something like, and I could use a byte oriented register here if I wanted to, and I guess we could do that. Let's use AL. And we'll go ahead and get a value out of hex digits plus REX. So I'm going to use REX here as an offset into hex digits, getting one of these values because it's 0 to 15. It has to be because of that. And I'm going to put it into AL, which will overwrite that, but I think that's okay, right? Do I need to provide a hint here to the assembler to tell it I want a byte? This is a byte-oriented register, so probably not. It'll know I want a byte. All right, that's good. Now, that gets the byte in there. So now what I want to do is to put that in the correct position in this buffer. Where should it go? If I'm going to call write on the buffer, then I really want to fill from the far end. So let's see here. Right now, RCX holds what? It holds the number of digits to print. And if I take buffer and I add that to it, add the current value of that to it, yeah, that could work. Okay, so what I might do now is move into buffer plus RCX AL. Now, what's going to happen? Well, RCX, remember, holds the number of digits. So we'll never be at position 0, right? Because we'll always be at the lowest will be 1. So really, what I might do is subtract 1, so that now I would actually get position 0. So let's say that we come in here and I want 2 digits. So I will set RCX equal to 2. I will come in here, I'll pull one of the digits out, convert it, and I'll put it in buffer plus 2 minus 1. So that'll go in buffer buffer index 1. Then I'll decrement RCX and go through this again. Now it's 1. So buffer plus 1 minus 1 is buffer 0, buffer offset 0. Then I will decrement it at 0 and I'll stop. So that seems right. That seems like the right thing to do. In fact, if I want a new line at the end of it, it seems like what I should do is right up here, before I get into the loop, I can move to buffer plus RCX the byte 10. So that'll put a new line at the end of this little space here, because I'll never come to this position, right? Because RCX is always being decremented, and down here I'm always subtracting 1. So that works out well. I like that. That seems reasonable-ish to me. So now it's in the buffer, and so now I need to decrement RCX, and if it's not 0, go back to the top. And there's an instruction that does that, and it is loop. So loop will decrement RCX, see if it's 0, and if it's not, go back to the top. Now keep in mind what happens. It decrements it first, and it decrements it no matter what. And then if it's 0, we go back to the top. So assume we are at 1 on entry. We'll do this whole thing with RCX equal to 1. We'll decrement it, it'll be 0, and we'll stop. So we never go through this loop with it equal to 0. All right, that's great. So now, presumably, I've copied everything into the buffer, and I start at the 0th position. And how many positions do I use? I use a number of positions equal to what was in RSI, and it's still in RSI because I haven't used RSI in here, which is great because now I should be able to print it. So what do I need to do to print? I need to move RAX 1, so because that's the right function. I need to move RDI, and what goes in RDI? I believe RDI. See, this is tough. I need to go back and take a look. Let's go take a look. So we'll hop out into our browser. We'll go to the Chapman Linux System Call table, and we'll look at this first one right here, which is right. And it looks like RDI is the file descriptor, RSI is the buffer, and RDX is the count. So file descriptor, buffer, count. Great. So file descriptor goes in RDI. That's 1 for standard out. The pointer to the buffer goes in RSI. So how do I put the value of that in there? I can just do move RSI and buffer. That'll do it. Because the assembler will replace that with an address. Actually, it technically won't. The linker will do that, but don't worry about that. And then I need the count. How many things do I want to write? Well, I want to write, let's see, if I had 3 digits, I'd want to write out those 3 digits. But really, I want to write out RSI, right, +1, so I get the new line. So can I just put what I really want to do is do something with RSI. But I'm kind of in trouble now, because if you look, you'll see, oops, I modified RSI right here. Bad. So I'll go up here, and I'll move into RDX, move into RDX. I want to move in RSI +1. But I can't do that. They won't let me do that. But there is a trick I can use to actually do what I'm showing you right here, which is I can add that and change this to LEA. So now what that will do is it will take the value of RSI, it'll add 1 and put that in RDX. And I do that right before I overwrite RSI right here. Great. So now I can do my syscall, which should write this out. And then I restore the stack and I return. Now, did I do the right thing for the system call? I believe so. RAX is fair game for the callee. RDI and RSI are, as is RDX, right? So I believe I'm all okay. I'm within the confines of the calling convention, and I've written my little hex thing. Now I don't put underscores in. I'd like to do that, but I don't do that yet. So let's go ahead and see what happens when I try to assemble this. Boom! I get something that looks like it's been assembled. So now what I need is some code to test this. And I'm going to write C code to test it. And let's just call it test. And so I will need a little make line for that. So let's put a make line in here. And what I'll want to do first is make hex.asm. And if that works, then I'd like to go ahead and GCC. And what I want to do, I want an output, which is equal to the base file name of this file. So it'll just be called test. And I want to include this file, which will get compiled, and then I want to also link with hex.o. There we go. So let's go ahead and include standard IO because I want to use print, and let's go ahead and include int types.h because in case I need them, which I may not, and let's say int main int argc char star argv array char star envp array close open, and we'll have just a line that invokes hex here. So we'll say print hex. Let's give it a hex value to print. 134. We want 3 digits printed, and that's our line. And then of course we can turn 0, and there we go. Now the compiler's not going to like that because it doesn't know what print hex is. So let's go ahead and give it a prototype. And so print hex will look like the little prototype we had in the file before. So we're going to say u int 64 underscore t value and u int 64 underscore t count. Now we don't actually need to specify names for these. I just did that here, but the prototype doesn't actually need them. Right? The prototype only needs to know the types. Get rid of those. There we go. Nice and simple. And we say int 64 underscore t here, but really we could use something else here if we wanted. There we go. So let's go ahead and see if that looks right. Looks right to me. And let's do a make of test.c and see what we got wrong. And it looks like it wants to complain. And it wants to complain about something called this relocation. So what's happening here is interesting. It wants to make a position independent executable. And I don't want to explain that to you right now. I'd rather just go in here and make one little change up here, which is to make this a statically linked program. And we'll get a warning because we didn't include this little guy. Now we can fix that. There we go. Get the right thing out in a minute. Okay. And now we'll do a make, and we get no errors. So, and no warnings. So, do we want to actually run this? So we have a little thing called test. It's large because I statically linked it. I statically linked it because I don't want to explain to you how to build a position independent executable just yet. We will get to that. And let's just run test and see what happens. And what happens is we get the right answer. So that was kind of unexpected. So let's go ahead and vim test.c. Let's try some other stuff in here. Let's print out 134, but let's print it out with 8 digits. And for fun, let's also do a print hex of 0x hexadecimal 98765432116. That should be the most we should be able to do, and that should work. So let's go ahead and give that a try. So we'll do a make test.c, and then we will run it. And look at that. 134, 1, 2, 3, 4, 5, 6, 7, 8, correct. And then look at that. hexadecimal 98765432110. It worked.